let's begin. We have investigating PowerShell attacks with Ryan Kazanciyan and Matt Hastings.
Good afternoon, all. Thank you so much for coming to our talk this afternoon. I'm Ryan Kazanciyan, Technical Director with Mandiant. I'm here with Matt Hastings, one of our consultants and investigative leads. And yeah, welcome to the talk. So just to make sure that we're all in the right room, this is investigating PowerShell attacks. This is not investigating these blue shell attacks. So just so that we're clear, different blue shell, same deleterious effects. So what got us started on this? So we've actually seen quite an uptick in the use of PowerShell during targeted attacks throughout the past 2 years, I'd say, at Mandiant. Matt and I actually worked a case this year between January and April in which the victim's VPN had been compromised by an attacker for about 3 to 4 years. And the attacker was almost exclusively conducting command and control from their own system over the VPN to the target hosts through scheduled tasks, a couple locally copied PowerShell scripts, and PowerShell remoting, which is basically PowerShell over the network. And what we came to see is that when an attacker is good at this, it's really, really hard to reconstruct what they did on the endpoint system. And so that kind of was one of the impetuses for us to begin this research. We're not in this class, the course of this presentation going to explain how PowerShell works or all the things you can do with it. Suffice it to say, if you're not familiar with it, it's an incredibly powerful command line and scripting environment. It can do almost anything from basic remote command execution or local command execution to actually invoking or accessing the entire .NET framework, loading and executing code in memory, interacting with the Windows API. So it's incredibly powerful. And a number of PowerShell attack tools have been built over the years that kind of take advantage of this. And one of them was at Arsenal Today, written by one of our colleagues, Matt Graber, as well as Joseph Bialik and Chris Campbell, some great PowerShell researchers. PowerSploit. PowerSploit is really awesome. It does DLL injection. It can run Mimikatz in memory on a remote system. It has all sorts of cool features, and we have a few other listed here, but the bottom line is this is being integrated into a lot of attack toolkits, both commercial and custom. We're also seeing, in addition to targeted attackers use it, commodity malware use PowerShell. The first PowerShell worm was kind of a proof of concept. It actually came out in 2006. Now we're actually starting to see some real non-proof of concept mass malware that integrates PowerShell into their payload. So what we wanted to do is strip away the specifics of is this commodity or is it a targeted attack and kind of boil it down to the root of PowerShell and its most fundamental use cases and how that impacts the system forensically. So we took 3 base cases as the foundation of our research, running a PowerShell script locally on a system, using PowerShell remoting, which goes over the WinRM protocol, and having a PowerShell script or code that is configured to be persistent on an infected system. And for each of those scenarios, we looked across disk, the registry, file system metadata, memory, as well as network traffic to understand what sources of evidence were left behind. And that's kind of the crux of our work that we'll share with you today. One assumption, we're talking about the use of PowerShell in a post-compromise scenario. And for us, in the majority of cases we work, that means attacker has already popped the domain. They either have local administrator access on a number of systems or, inevitably, domain administrator rights. And what that means is that all of the security controls that are in place to kind of limit malicious or unintended use of PowerShell don't matter because they can be bypassed by the attacker using their privileges on the Windows host. Finally, we're going to mention throughout this presentation a number of different versions of PowerShell. What is most prevalent in enterprise environments is 2.0 because that's installed by default in Windows Vista and Windows 7 as well as Server 2008. PowerShell is now up to version 4. This chart kind of shows you what's by default. The reality of the situation is that because PowerShell 3 and later requires an optional update, we expect to see PowerShell 2 be the default version that will be available in corporate environments for quite a while because companies aren't going to be rushing to upgrade their entire estates to Windows 8 and Server 2012 R2 immediately. So a lot of the evidence we're going to provide is within that context. So we'll begin by talking about memory analysis. So with memory analysis, we wanted to look at the worst case scenario, which is An attacker interacts with a targeted host through PowerShell remoting and doesn't put anything on disk. So they're not copying a script to the remote host. They're simply using remoting to run commands, run code, kind of like the invoke Mimikatz feature that PowerSploit lets you do, the worst case scenario where you're not touching disk. To understand how remoting leaves a forensic impact behind in memory, we have to understand the process structure that's involved. So svchost.exe, the service hosting process that is launching or running the DCOM launch service, upon initiating remoting to an access system, let's say I use invoke command to run an external binary evil.exe. That instance of svchost will launch an instance of wsm-provhost.exe. And that in turn will launch evil.exe, so you'll actually see that it is a child process of wsm-provhost, which is a child process of that instance of svchost. In contrast, if I use native PowerShell commandlets like get child item, or if I'm running a PowerSploit module that's running over the network, instead of spawning executable, I will get another instance of wsm-provhost, but the PowerShell code runs solely within its context. In other words, PowerShell.exe will not instantiate on the access system. So what's left behind in memory? While wsm-provhost is running, there's actually structures from the PowerShell object format that contain the entire history of that PowerShell session. And if you dump memory of wsm-provhost, you'll see them clear as day. The problem is that wsm-provhost terminates the moment a PowerShell session exits. So if I run a single remote command, the moment that command ends, that wsm-provhost terminates. If I use enter ps session, like psexec kind of functionality, and I have a persistent session, the moment I exit out of that, wsm-provhost is gone. So you lose that history. However, what we did find is that another instance of svchost that is hosting the WinRM service actually retains remnants of remoting activity even after a session has exited. How long it retains that depends on what the volume of remoting connections a system processes are, but in some cases we found that all the way until reboot, remnants of commands might stick around in its memory. We also found trace bits of PowerShell remoting in the kernel as well as page file. And what we have here, I'm not going to read through the entire thing, is a table that kind of compares these different sources of evidence in memory and how long the evidence is retained. But the bottom line is svchost for the WinRM service is your best bet for recovering some of this evidence of remoting activity. Now, what it looks like is in memory is a little difficult to eyeball or search. What you're actually going to find in WinRM memory is the SOAP structures that PowerShell remoting is encapsulated in when it goes from one host to another. And so in this very simple example, I have a PowerShell commandlet to echo a string to a file, and I have a snapshot of what we recovered in memory from the WinRM service process. And you can see around all of this XML, and I apologize if this is hard to read, you can see the exact command that we ran. Similarly, we use the invoke Mimikatz module in PowerSploit to remotely run, in fact, download the script and run it in memory without ever touching disk. And again, on the target host, WinRM service memory retained the entire command that made it very obvious what happened for many, many hours after the activity occurred. If you want to find this in memory, I think one day this might be a good candidate for perhaps like a volatility module. For a string search perspective, what you're looking for are remnants of the PowerShell remoting protocol, PSRP, or remnants of the strings that encapsulate or surround the commands in the SOAP XML. And so by looking for some of these like RSP command and RSP command line, you can find traces of commands and or their output. So really with memory analysis, timing is everything. It's really hard to recover this evidence, but it is in memory. We just wanted to define what was available and for how long. System uptime, memory utilization are all variables that are going to impact this.
Thanks, Ryan. So when we looked at event logs, we tried to cover two key scenarios, both of which is when an attacker is interacting with the system both locally and remotely using PowerShell, and try to answer three key questions. The first being, which event logs are even available to us, and what type of information are going to be found in each one of the logs. And then finally, and I'll go into more detail in this in a few slides, is really the differences between PowerShell 2.0 and 3.0 and what you can see between the two. So in total, we identified 5 potential candidates for where PowerShell activity can be recorded in the event logs, and I have them listed up here. In all instances, activity is not going to be written to each log, but we'll go through multiple scenarios looking at local and remote execution, and we'll highlight some specific EIDs that we found useful. So first, looking at local PowerShell execution and the PowerShell log itself, we identified 2 events, event EID 400 and EID 403, that recorded specific execution time. So in EID 400, the engine state changes from none to available. This indicates that activity has begun. And so if you look at the generated time of this event, you can deduce, okay, this is when PowerShell actually started running. Similarly to EID 403, this records the stopping of the PowerShell engine. And so taking these 2 times, you can say, okay, this is roughly how long PowerShell is running on the system. And looking at the hostname parameter written with this event, you can see here a console host that indicates a local session. We'll show you in a further slide what a remote session actually looks like. The PowerShell operational log really in 2.0 doesn't record any additional information that we found forensically useful, but EID 40961 does record the PowerShell console starting up. So again, nothing new here. One caveat though, in PowerShell 3.0 and greater, the operational log does record some errors. So here we see the script ctemp_test.ps1 failed to run. Similarly, if you fail to connect to a remote system, that will also get logged here. So you can see the remote host name or IP address that PowerShell failed to connect to. Finally, the PowerShell analytic log, and before I go into this in too much detail, analytic logging is disabled by default, and probably for good reason. Once it's enabled, it generates a massive amount of events and is not really meant for long-term sustained logging. But if you do enable it, at least on PowerShell 3.0, you can get specific command execution. So here we can see in the same event ID, we see test.ps1 is started. Specifically then write host, any commandlet that you would run within PowerShell is also captured. And finally, if you run an executable through PowerShell, that's also being logged. A big caveat here though, and something that we can overcome later in PowerShell 3.0 is this isn't going to capture any event arguments. So you're just going to see what is run and not the context in which it's run. Moving now to PowerShell remoting and back to the PowerShell event log itself. The first EID 6 is actually a message that's recorded on the caller system, so where you're running the remote command from. You see here that it's recording creating the WSMan session. So WSMan is the protocol used within the WinRM service. And so this indicates that a remote session is beginning on the remote system. And similarly, back to the PowerShell log on the victim, here we see EID 400 and 403 again recording the start and stop of the PowerShell engine. And here you see the host name is server remote host, indicating that it was a remote connection and not local. The WinRM operational log, again, this is specific to remoting because PowerShell utilizes the WinRM service, so obviously events can be written to the WinRM log. Here you see EID 169 actually records the specific user and security protocol that's used to authenticate. So here you see Matt H is using NTLM to log into the system. And then similar to the PowerShell log, you can deduce the length of activity looking at EIDs 81 and 134. Going back to the PowerShell analytic log, I did mention that it generates a lot of events, and it certainly does, but it does capture specific commands that are being run on a system, just in an encoded format. So here you're also seeing in event ID 32850 the specific username that's being authenticated, and then finally in 32867 and 868, you're seeing the specific payloads being every payload being sent and received to and from the remote system. And this will include both the protocol negotiation that happens at first and then every single instance of data being sent back and forth to and from the victim machine. And it's all in an encoded format. So if you look, it really doesn't give you anything. You don't, just by default, you'd have to copy this all out and decode it. So here's an example command being sent, just saying to get the child item of C, which is basically just ls on the C. So once you decode it, here you do actually see specific commands being run with arguments. So here the command is get child item. It's not a script, and it's being run on the C directory. And here we have an example of the response being sent back. And one thing to remember is in PowerShell, running specific commandlets causes all responses to be sent back in the form of an object. So every time, or every single specific directory or file within the root of C is going to be sent back in a separate or recorded in a separate event log as an object, and you're going to see all of this information. So a single command being run remotely is going to generate a large number of events. Each one has to be decoded, and it's really not practical to do so. Another option that you can employ, specifically with PowerShell 2.0 that we've seen a lot of some companies use that I know Ryan's worked with specifically, is the global profiles. There's a number of profiles that PowerShell utilizes that will automatically load on local PowerShell startup. So again, this is only to local PowerShell usage, but using the built-in command like start transcript or even writing some custom code, you can capture all commands being written to and then the responses from the shell. Now, there's some limitations here, one of which I mentioned earlier. This is only for local execution, and also you can actually bypass this fairly trivially with just setting the no profile flag when you're running PowerShell, and nothing here will be loaded. Also, if you're using AppLocker, you can set AppLocker to either audit or enforce script execution. So here we have an example where it's actually recording the time and the path that a PowerShell script was run. So this can definitely be useful too if you're using AppLocker. And then finally, this is the true solution that we found and we recommend, is upgrading to PowerShell 3.0 and implementing module logging, which writes detailed command input and output to the event log in clear text. And every single time a command is run for PowerShell, it creates this event. And we'll see how that's a good thing and then how that's a bad thing in a couple slides. And again, this is just a quick example of how you can configure it. So in this next example, we actually ran a little bit more complex command. So we're looking at the ctemp directory, recursively looking for specific files that have a .text extension. And then we're running basically a grep, which is select string in PowerShell, looking for the term password. So the top event here, we're actually seeing all the commands being passed with the specific argument being logged. And then finally, you're seeing the output here on the bottom. And again, this is all logged in clear text. So in our next example, we actually use the PowerSploit module and with invoke Mimikatz. And like I said, every single time a PowerShell command is run, it generates an event. So a single instance of running invoke Mimikatz generated over 1,200 events. So practically, it's not practical to parse through them all. However, if you do find the resulting output, it's actually pretty funny. You can see the Mimikatz output in clear text here in the event log.
All right, and finally we're going to talk about persistence. And of course, persistence is a common goal that attackers have when they want malicious code to keep running, even surviving system reboot or user log out and log on. So we're going to talk about some common persistence mechanisms that can be used to persist malicious PowerShell code and how to find them. Actually, one of the things that's covered by some prior research is that you can use any of the existing persistence mechanisms in Windows that are very well known and documented, like registry auto start locations, recurring scheduled tasks, the user startup folder. I mean, really all you have to do is invoke PowerShell.exe and give it a script argument. So we're not going to talk about those because that's kind of basic stuff that malware has exploited for persistence in Windows hosts for many, many years. I do want to cover, though, one thing that is kind of specific to a way that PowerSploit can persist malicious PowerShell code, and I also think it's a more sophisticated mechanism that is well suited for PowerShell, and that's WMI, or the Windows Management Interface. So WMI is this incredibly complicated thing that has this eventing infrastructure where I can register these event filters, which basically constantly query for different types of events, and when they trigger, you set up a consumer that's bound to it, and the consumer runs whatever you tell it to run. So using PowerShell itself, we can create these event filters and consumers and make them do bad things. So an event filter is what causes a consumer to trigger. So if you were an attacker and you wanted to create an event filter that would achieve your goal of persistence, you might do something like create a WQL query that runs within X number of seconds of startup. Whenever that is satisfied, the code runs. Or you might set a filter that runs something at a specific time. These are actually both of the default options that the PowerSploit tool's persistence module provides to you. So once the filter runs, the next step is something has to consume it, consume the event and do something, and that's where we actually run PowerShell.exe. So the trick here is, where does the code come from? I need to do more than just run PowerShell. I have to give it code to execute, and I can do one of two things. I can either put it in the arguments to my PowerShell command line that will be fired by the event consumer. The constraint there is the maximum command line length allowed by Windows, which is like, I think 8,000 characters or thereabouts, which is plenty long if you have encoded code that's being decompressed on the fly. The other option is you can just put the code in the PowerShell profiles, and then the moment PowerShell.exe executes via the persistence mechanism, it will load from the profile and it will automatically run. Finding this can be a little tricky. Actually, the best way to enumerate WMI filters and consumers and determine what's installed is to use PowerShell itself. The get WMI commandlet will allow you to enumerate filters and consumers. And we found that it's very easy to baseline in your environment and determine with your default OS image what consumers do and do not exist. And in most environments, they're not going to have consumers to automatically run PowerShell. Certainly not with arguments to execute code. On the file system, when you create a WMI event filter or consumer, you modify the WMI repository, which is in this WBEM directory. These are undocumented and very complex files that you can strings, and if you strings them, you'll see remnants of the consumer name or the filter name and remnants of the command line, but not easily suited for analysis because as of now, there's absolutely nothing out there that will decode and parse these files from a dead disk image of a system. You can also inspect the user profile. I think a good forensic step is to look at every profile.ps1 on a system to ensure that there is no malicious code in it. And then finally, we noted that when you use certain types of event filters, it creates a registry key which is otherwise not present on a default Windows image. So for example, in the case where we created an event filter that fired at a specific time of day, that creates this registry key shown here for Win32 clock provider. And in investigating large environments and checking this key across tens of thousands of systems, we found it's only set when an event filter is created that triggers in a specific time, which is, I think, intrinsically kind of suspicious. There are other tools you can use. Sysinternal's autoruns was recently updated to enumerate the WMI repository. You can find references to PowerShell there. There's also WMI trace logging, which you can enable, but it's incredibly noisy. So it will record the creation and execution of filters and consumers, but on a normal Windows system, that happens constantly. So I don't think it's a reasonable target for investigative use.
So we're almost out of time, so I'm going to go pretty quickly through this slide. We certainly didn't cover every single source of evidence that's possible on a specific system. We do, however, cover a lot more of these features in our white paper, which should be made public either sometime today or shortly later this week. But if you are looking at, let's say, a Windows workstation, looking at the prefetch file created for PowerShell.exe can sometimes provide you useful information. Now, again, this is only for local execution of PowerShell, and then looking at the access files list can sometimes provide you either, hey, was a PowerShell script run, or did the PowerShell activity access files that I might be interested in. And then another core place is the registry. Ryan mentioned a key on the last slide, but also looking at the execution policy of PowerShell. A lot of times it's set so that only signed scripts can be run. Again, you can bypass this very easily at the command line itself by setting the script execution policy to bypass. But actually, in one instance, Ryan and I observed an attacker modifying this registry key. We have no idea why they would do this because, again, it's just a command line switch, but it is useful in looking at. And then finally, looking at network traffic analysis, specifically for the WinRM service, PowerShell runs over port 4985 or 5985 and 5986 by default. However, regardless if it's running HTTP or HTTPS, the payloads are always encrypted. HTTP just gives you some of the version information and some of the headers. And then just looking for anomalous NetFlow activity. And finally, just some of the lessons learned and some of the tips that we'd give. First and foremost, upgrading to PowerShell 3.0 or later and enabling module logging is your best bet on a single source system of capturing specific commands being executed. Beyond that, though, kind of looking at a higher level across an enterprise is baselining legitimate PowerShell usage. So looking at registry keys and your execution policy, how do you name your scripts and where are they always located? Do you run remoting? If you are running remoting, who are the users that should be running remoting and what subnets are they running them from? So baselining that and then looking for anomalies is a really good way of detecting malicious PowerShell usage.
Thanks. So yeah, in closing, we just wanted to acknowledge a lot of the researchers and coworkers that have helped us out with this work, as well as done some of the groundbreaking research in use of PowerShell for both attack and defense. I'd also like to thank a lot of folks at Microsoft, like Lee Holmes and Dave Wyatt, who supported this research quite a bit. I will say that From their perspective, it's a challenging situation because, again, if someone has administrator on a Windows box, all bets are off. That being said, they are aware that there could be better ways to monitor usage of PowerShell, and I've been told that there are going to be some things coming down the line that will make it even easier with what's built into the operating system to monitor stuff, because the fact of the matter is attackers are going to continue to learn how to leverage this, and we expect to see more and more of its usage. So as Matt mentioned earlier, getting that baselining done and starting to understand how PowerShell is, if at all, legitimately used in your environment will give you a big leg up when you have to start tracking or monitoring for an attacker's use of it. If you have any questions, once again, the white paper that we'll be releasing has a lot more detail. Also, please feel free to either email Matt or I, or you can reach out to us on Twitter. But thanks again for attending. I'm not sure if we have time for questions. Okay, I was told no, so we'll be around, so grab us if you have any questions. Otherwise, enjoy your conference, and thanks again for coming.